So there's one more type of problem that we're going to focus on factoring, and then we'll just kind of mix them all up in our next lesson and make sure that we're ready for all of them. But so it's called difference of perfect squares, and to see what that means, we're going to do these two problems, and you'll see how they end up with different products, different patterns, and again, what we're looking for are those patterns. Okay, so notice here what we're going to multiply in this case is I'm multiplying the same binomial, right? I could write this if I wanted to as x plus 3 squared, right? This is really, I'm taking the same thing and I'm multiplying it by itself, so it's x plus 3 squared. And when I multiply this, you should already kind of have an idea of what pattern to expect, right? So I'm going to go x times x, I get x squared, and I'll go x times 3, and I'll get 3x, and then I need to distribute the 3. So now 3 times x is plus 3x, and 3 times 3 is plus 9. And again, same as normal, we have to combine these like terms. So I get x squared plus 6x plus 9. And this fits the pattern that we've been looking for, right? We knew that this number right here should be 3 times 3, and it is. And then we knew that the 6 should be what I get if I add these two numbers, and 3 plus 3 is 6, right? So 3 plus 3 is 6, 3 times 3 is 9. It's exactly what we've been expecting. That's the pattern we keep seeing, right? So I take two binomials, multiply them together, and my answer is a trinomial. That's what we've been seeing. You should expect that. But now watch this one. I still have two binomials, but notice this little difference. I have a plus in one, and I have a minus in the other, but everything else is the same. I have x, and I have 3 and 3. Everything else is the same, except for that plus and minus. Now when we multiply that, watch what happens because of that. So x times x squared, same thing. X times negative 3 is minus 3x, and then distribute this, plus 3x. And 3 times negative 3, careful, is negative 9. Okay, so now when I combine this is the key. Watch what happens. I have a minus 3x and a plus 3x, ready? And the minus 3x came from having this minus, and the plus 3x came from having this plus. But when I do that, that's 0, right? Those cancel out. So I get nothing, and I could just write that, right? Those are plus 3x minus 3x is 0. So now I just have my x squared and minus 9. So where did that middle term go, right? We're used to this middle term. And the reason we don't have a middle term here is because the plus 3x, which I got from multiplying the 3 times an x, and the minus 3x, which I got from multiplying the negative 3x, canceled each other out, and so you end up losing that middle term. So what you need to be on the lookout for now is this. This is what we got to have our eyes open for, and this is called a difference. And the difference is because it's a minus sign, right? Difference just means subtraction of perfect squares. And by perfect squares, we just mean that x times x squared is a perfect square, and 9 is a perfect square because it's 3 times 3. So this is what we're looking out for. And so when we see this pattern, a difference of perfect squares, we can factor it. We know that what we multiplied to get it, were two binomials where the numbers were the same, 3 and 3, but the signs were different. The signs were plus and minus. If they were the same, then we would have ended up with a middle term. The only way that they're going to drop out is if it's plus 3 and minus 3, or some number, but it's the same number and different signs. So now let's go see. We're going to look for that pattern in a couple more examples. So again, I notice right here, again, I'm on the lookout for this. This is a difference of perfect squares, right? The difference, because it's subtraction, y squared is y times y, and 25 is 5 times 5. So right away I see, oh, I've got a difference of perfect squares. And so I know what I must have multiplied together to get it were two binomials, y times y, where the numbers were the same, 5 and 5, and the signs were different. And I can multiply these, I can distribute it just to confirm that we would actually get y squared minus 25 when we do it. So y times y is y squared, y times negative 5 is minus 5y, 5 times y is plus 5y. You can already see they're going to cancel out, and 5 times negative 5 is negative 25. And again, these cancel out. That's why you have no middle term, and you just have the y squared minus 25, which is exactly what we got. So we know that this is what we get when we factor it. So when we see difference of perfect squares, right away we should think, right, 25 is 5 times 5, and y squared is y times y. And the reason there's no middle term is because one was I didn't mean to get rid of that, was because one was a plus and one was a minus, okay? Over here, what you can see is we can get a little more tricky with these because you're thinking right away, okay, well, that's 9x squared, but 9's also a perfect square, right? So 9x squared I could get by going 3x times 3x, right? X times x will give me the x squared, and 3 times 3 will give me the 9. So even if it's a little trickier than that, it's still fine. And now you're thinking, well, 1, over here is 5 times 5 is 25. That's fine. But 1, what times what equals, well, 1. 1 times 1 is still 1. That's why 1 is still a perfect square. So right away I'm thinking, okay, I must have had two binomials. And in this case, it's not just x, but it's 3x, because the 3x times 3x will give me the 9x squared. And then I know 1 times 1 will give me the 1. And then again, the key is these signs have to be different. If they're not different, you're not going to get what you want. And we can still distribute it this just to check. Make sure, right? 3x times 3x is 9x squared. 3x times minus 1 is minus 3x. 1 times 3x is plus 3x. And 1 times negative 1 is minus 1. And again, this crosses out, and we're left with just 9x squared minus 1, which is exactly what we started with. And that's how we can check to make sure that we factored it correctly. But keep an eye on the patterns, right? What are we looking for? When we see something like this, where there's no middle term, and the number is a perfect square, and the y squared is a perfect square, or even over here, something a little more complicated, but there's no middle term, but the y, that is 3x squared times 3x squared, right? The number 9 is still a perfect square. And 1 is 1 times 1, right? That's what we're looking for. When we see that, we know that that's a difference of perfect squares. So let's do two more quick ones. We'll actually start on the right one, the easier one, and we'll move back to the left, right? So I see this, and I see, oh, that's n times n. That's a perfect square. And 36 is 6 times 6. That's a perfect square. So I have a difference of perfect squares, and so I'm just going to put my binomials in. I know it's n times n. I know it's 6 times 6. And I know the key is that these signs have to be different. And that is my answer. And if I want to check, I just go n times n is n squared. N times negative 6 is minus 6n. 6 times n is plus 6n. And right away, I'm just going to do it right now. They cross out. And then 6 times negative 6 is minus 36. And sure enough, we get exactly what we started with, which means we must have factored it correctly. Over here, again, x times x will give me the x squared, but what about that 49? Well, that's just 7 times 7. So I know that 7x times 7x is going to give me 49x squared. And that's what we mean by perfect square. It just means we took the same thing and multiplied it by itself. It's a perfect square. All right, and then the 9 is just 3 times 3, right? I'm looking out for those perfect squares. And so I know I'm going to have my two binomials. I'm going to have 7x, in this case, a little trickier, but I'm going to have 3 and 3. I need different signs, a plus and a minus. If I wanted to check it, I could. And maybe the last thing we'll do is just, what are the perfect squares, right? So what do you mean by perfect squares? I just mean 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. 5 times 5 is 25. 6 times 6 is 36. 7 times 7 is 49. 8 times 8 is 64. 9 times 9 is 81. 10 times 10 is 100. Usually those are the ones that you're going to work with most often, but that is what we're looking for. We're looking for those perfect squares. So you're looking for those numbers. If you see those numbers, that should be a warning bell should go off right away that you're talking about a difference of perfect squares.